Good afternoon, everyone. The title of my talk is Joint Geometric and Photometric Wave Tracking based on Lie group. These are the joint workers, Shi Zelin, Liu Yingpeng, and Liu Tianci. First of all, for people who are not familiar with direct visual tracking, I will briefly explain what goal is. Usually we select an tempo in the first frame of a video. The goal is to track the tempo precisely in the following frames. Here we want to find a geometric transformation and a photometric transformation such that the two images can be matched as closely as possible. This problem is often formulated as an optimization problem, which is often solved through Lucas-Canada framework. Previous methods include three types. Parametric methods usually based on SSD mirror. DRC is efficient, however, with small convergence radius. ESMPA algorithm has larger convergence radius, however, is not efficient to elimination changes. Invariant methods use robust mirror instead of SSD. They are robust to elimination changes, however, at the cost of high computational cost or small convergence radius. Recently, dense descriptor combined with Lucas-Canada framework has been proposed. However, even though they are very robust to elimination changes, they has much higher computational cost. Our work is motivated by DIC and ESMPA algorithms. DIC model both of the geometric and photometric transformations in non-Euclidean Lie group. Only the first order approximation is used. In ESMPA algorithm, the geometric transformation is modeled in non-Euclidean Lie group. However, the second order approximation used. In our methods, we combine the advantages of these two methods. We model the geometric and photometric transformations in non-Euclidean Lie group and used the second order approximation. This results in more efficient and robust methods. In our methods, the photometric transformation is represented by the gain and bias model. This is a affine transformation and can be modeled in affine group. The geometric transformation is represented by the projective transformation and is modeled in special linear group. Therefore, our problem is defined in the joint Lie group. Sorry. This can't show. Okay. The joint Lie group is parameterized by their joint Lie algebras. The problem can be explicitly writing as this problem. Theta is the joint parameters. The D is the error function. Here we give it a second order approximation. These are the Jacobi matrices. Note that the approximation is second order, however, it remains linear form. Here, the Jacobi is based on the unknown parameter theta. Because we use Lie algebra parameterization of geometric and photometric transformations, these Jacobis can be computed as this. Therefore, our problem can be approximated by the linear least squared problem. The solution is given by the normal equation. Then we update the initial geometric and photometric transformations like this. The integration process is stopped until the solution is smaller than a given threshold. Here we give the experimental results. We evaluated our methods on synthetic data and real data. Our method is compared with these 4 methods. We select 6 emitters for synthetic experiments. These emitters contain different types of contents. And this is a comparison and the different geometric deformations. The horizontal axis shows geometric deformation magnitude in pencils. The first figure shows the number of intuition, and the second figure shows the convergence frequency. It can be seen that our method always has the lowest number of intuition and the highest convergence frequency. Particularly, compared with DIC methods, our method is much robust than DIC. This is the comparison and the elimination changes. Here we vary the gain of the photometric transformation. From the first figure, it can be clearly seen that our proposed method has the lowest number of iterations. The red line is ours. The second figure shows the convergence frequency. Other methods except the SCV methods are very robust to photometric transformations. Next. Here we give some tracking results on real video. We select 3 videos containing standard illumination changes and low light. The red box is ours. Okay. This table lists the average number of iterations and runtime per frame. In these real data experiments, our methods can successfully track the tempo in all the 3 videos. NA means tracking failure. Our method is the lowest iterations and runtime. Here is the number of iterations. This is the runtime per frame. In conclusion, we have proposed an efficient and robust video tracking method, which can cope with large geometric deformation and sudden elimination changes, based on the joint Lie group representation and the joint Lie algebra parameterization of geometric and photometric transformations. Thank you.
So, is there any question?
Yes, I have 2 questions. Okay. First, why do you take SL3 for the photometry? Because it could be also something which translates. Okay? If you have color, the 3 dimension in photometry are because of color. No, when you take SL3 at the beginning, to the right. Yeah. You have affine. It is for photometry. Yeah.
The photo
to the right, the SL3.
SL3.
No, because GA1 is for
GA1.
the deformation of the picture.
This is we use this to model the photometric transformation.
Yes. So why do you don't have a translation, possibility of a translation. Because in space of color, you could also change the mean, no? Yeah, you fix the origin. So, of course, we say after. No,
sorry.
Another question. Do you have time? Because GA1.
GA1.
In your demonstration, at the end, when you show the movie, the GA of 1, the affine group. Okay. The affine group, yeah.
Affine group.
No, because, yeah, that's absolutely. That's why my question, absolutely. Because it's more natural to have an affine transform in photometry.
Sorry.
And a projective transform, not projective transform on the image. Yes, absolutely. It was my second question. Okay, why you don't take projective for the image? Yeah. Okay. Okay, thank you.
Any question? Okay, so let's thank the speaker again.
Thank you.